Thank you all, and welcome to the first 3DHP for the Nation Forum of the year. We had great response. Matt Baker is going to be talking to us about high resolution hydrography using Geomorphons, which has generated a lot of interest. Just some quick revisit for those of you that are new. This is a NSGIC USGS cooperative agreement to look at the derivation of high resolution hydrographic data from 3D LIDAR, IFSAR, and Alaska. If you could please put your name and your organization in the chat. That helps us figure out who's interested in these topics. And you should be aware that the presentation is being recorded. I wanted to start this time with a little bit of project news. We do have the project year 2 in place. We're excited, January 1 through December 31st of this year. So lots of new and exciting things happening there. You may have noticed in your meeting invite that the forum's been extended to 1.5 hours. We are going to work with the presenters to try and keep the core content to 1 hour, but have that option for continued discussion in the last half hour, as we've always had to cut discussion off. So we're hoping this new approach will give us a little bit more flexibility. We mentioned last time we're going to be replacing forums quarterly with 3DHP interest group meetings. Those will be in March, June, September, and December. If you're interested in joining the interest group meeting, we have a little bit of information in the next slide or two. And in addition, if you're interested in presenting your 3D hydrography work, or if you have a specific topic you'd like us to address, just contact me and we can explore that. Just quick run over the activities, excuse me. First 2 activities here on the right, facilitate a monthly forum. That's why we're here. If you're interested in past forums, you can go to the NSGIC Learning link and do a search under 3DHP or EDH, and should be able to find past presentations. I should mention we do a Q&A doc at the end of each presentation, and those are very helpful resources. So I'd encourage you to go check those off. We mentioned that we have 2 communities at mynsgic.org. If you have a NSGIC registration login, which you should to register for this meeting, you can join either of these groups. There's the interest group, which is a general information, and we give project updates. Our next meeting is going to be March 16th. And then there's a working group. If you're interested in actually doing more hands-on work with project tasks, we invite you to join the working group as well. If you do join the working group, please join the interest group, because that's where most of the correspondence takes place. Other activities are the development of an inventory of state and regional 3DHP experiences, and Phil has developed a great inventory for us. I'll put the link in the chat. Phil, I'm going to have the link for the long one. Phil has created a shorter version, and hopefully he can follow up with that.
I will post it.
Can you do both of them, Phil, since I can't run my mouth and click at the same time?
Absolutely.
As good as I am at running my mouth, I do hit challenges now and then. If you would put both those in the chat, that'd be great. Thank you.
Will do.
We're also working on these 3D hydrography critical factors. I am this close to the refinement, and we'll be sharing those with USGS for a quick review. And the 3DHP working group, if you're a member of that group, you should be seeing a message soon to go in and take a look at them. We want to vet them with the group. That is our objective for the March meeting, is to be able to share those with the full community at the March interest group meeting. In response to those critical factors is the idea of identifying potential resources that could be used to address those critical factors. And that would be the next step. And our last task, and this is last year's project task, so we'll be updating this the next time we meet, is to establish a NSGIC 3DHP info hub. And again, Phil has got that, I believe, in the final stage. We'll be looking at it, in fact, tomorrow, and hopefully be able to announce that to you, to announce the availability. Again, that announcement will be made through the 3DHP interest group. So if you're interested in getting this information, please go back to mynsgic.org and join that interest group. I believe that's all the updates and news. I am very glad to introduce Matthew Baker, Dr. Matthew Baker. He's a professor with the Department of Geography and Environmental Systems at the University of Maryland, Baltimore campus. Matt, you said you're on detail right now?
I'm doing a tour in the college dean's office as an associate dean.
Oh, okay. Well, nice that we're giving you this opportunity to touch base with your real geographic roots. So
Thank you.
With that said, I am going to stop sharing. If I can find my controls. There they are. And I probably should have given you permission earlier, Matt, to share.
Participants should have permission, so it should work.
Okay, you should be able to go to the share. Excellent. Thank you, Dr. Baker. Take it away.
Okay, well, hi everyone. Thanks for coming today. Today I'm going to talk about methods that we've been developing in the Chesapeake Bay watershed in the eastern United States using Geomorphons for delineating high resolution hydrography from 3D products and LiDAR. The talk I'm going to give today is the result of work that I've been engaged in since 2017 with my colleague and collaborator, David Saavedra from the Chesapeake Conservancy and their Conservation Innovation Center. And more recently, we've been joined by a new postdoc in my lab, Shuezu Kang. The motivation of our work is really to try to look at the problem of and the need for new stream maps across the country, but specifically in the Chesapeake Bay Basin, where a lot of policy is driven by models based on stream maps. And for many years now, we've been looking at high resolution digital elevation data, which provide indications of channels in unprecedented spatial detail. And because we're in the Chesapeake Bay watershed, some of the jurisdictions often or have actually been collecting LiDAR with some temporal frequency. So we're able to look at changes in those signatures through time. And it's really clear that there are unmapped channels that are visible in the terrain data, but these channels often have characteristics that are somewhat distinct from the types of data that we've seen in the past, in that the channels have discontinuities. There are artifacts visible in the DEM from features on the ground. And because we have such a high level of detail, we can see infrastructure with a lot of clarity as well. One of the things that has occurred to me, I think I built my first digital elevation model in 1989. And I've been working in GIS for a long time. And it occurred to me that a lot of the tools that we have for mapping streams rely on sort of old technologies. The flow direction algorithm was really developed in the 80s that we used, and it was developed for a really different kind of DEM, where our perception of the surface was much more coarse and much more generalized than it is now. A lot of our algorithms don't integrate available information, so they rely on relatively simple or local pieces of information. And there have been few attempts to move beyond one-dimensional stream mapping, in other words, creating a blue line map and taking advantage of the multiple dimensions that are available in today's LiDAR data sets. Part of the other challenge that we faced was the challenge to automate our approaches. Right now, there's a lot of effort to map streams from LiDAR, but a lot of them are very time-consuming, labor-intensive processes that involve a fair amount of manual interpretation. And adding attributes to those data sets and conflating them with existing hydrography data sets is still a challenge. And what seems to occur is that the costs for doing that balloon over very broad extents. And such maps may also have a limited utility over time. So what we are interested in is looking at processes that we might be able to automate and make the line work available rapidly over very broad areas, and be able to redo them again and again as new information became available, or we wanted to refine the methods that we were using. So a more flexible and responsive approach to mapping streams. So what I'm going to talk about today is I'm going to start by just comparing and contrasting the evolution of stream delineation approaches in literature. This will be a very brief overview. Then I'm going to distinguish some of the key features in modern delineation techniques, what we call feature extraction, identifying channel-like features in the landscape, downstream tracing, and then adding attributes to those features. And I'm going to discuss, mostly my examples will come from the Chesapeake Bay watershed. More recently, David and I have worked in Pima County, Arizona, and also in Western Washington in the North Fork of the Stillaguamish River Basin, where we're exploring these techniques in really different landscapes with different climate regimes and physiographies. What I hope I'll be able to do is highlight some of the data product inputs, the refinements to the method that we've made, and the outputs, and then consider some of the new synergies we've discovered in developing this mapping technique. So when I started back in the 80s, the approach for thinking about delineating streams usually started with the DEM, and the first step we were told was we needed to fill sinks so that our DEM was hydrologically corrected. Then we could create a flow direction surface, build a flow accumulation surface, and use some critical drainage area threshold to develop line work. And apparently this is the technique that a lot of people still use today, some derivation of this approach. This was appealing because it relies on canned functions that are widely used and available in most GIS packages. It's interesting though, because in the days when I started doing this, the DMs were coarse enough, and the anomalies that you saw, the reason you filled sinks was that were really pits by and large, and they weren't huge areas that were being modified by such techniques. But these days, because of the detail we see in terms of infrastructure, it's possible for those sink filling operations and other terrain manipulations can really modify very broad areas of the landscape. The other thing about the DEMs of the day is that very few of them actually contained evidence of fluvial features. So we were mapping something that we really couldn't see. We only had an indirect indication of in the terrain. And a big problem was balancing errors of commission and omission, getting that critical drainage area threshold just right for any particular regional landscape. And that involves a lot of customization from place to place to place. With the advent of more available LiDAR, a number of investigators have explored changing that process. And they've introduced some new ideas into the terrain analysis and derivation of hydrography approach. And that starts with Pasalacqua et al. In 2010, although there are a few earlier attempts at this. And one of the things that they have in common is they all rely on some kind of terrain smoothing or denoising as a prep for the DEM to make sure that some of the signal is preserved and some of the noise that might disrupt stream delineation approaches are minimized. And then they typically involve some form of feature extraction using some detection technique to find channel-like depressions. And then they typically follow some kind of tracing algorithm, usually a flow direction surface, to connect features and to create a blue line network. These techniques have been fairly sophisticated. A lot of them are theoretical in nature. Very few of them have been developed for practical application. Pasalacqua's technique may be an exception to that. However, it's fairly process intensive. And my experience with it thus far is that it's generally was developed and best suited for natural terrain and struggles in a human-dominated or anthropogenically modified terrain. And these days, it seems like more and more of the landscape has either been historically or is currently under some form of modification. And so they're less appealing in my mind. One of the things about this description is that it kind of hides a level of detail in these approaches. So typically, there would be a couple of sub-steps here in the feature extraction. First, there would be some identification of depressions in the landscape, then some kind of thresholding to determine when you use a depression identification technique, which features were actually the depressions of interest, the significant depressions, if you were, and then, if you will, and then some form of filtering. That could be a size filter, paying attention to only larger features, or something about the drainage area under which they occur. And so all of those components went into a feature extraction algorithm. And then finally, for downstream tracing, a lot of the algorithms rely on a very similar approach to what you see on the left here, where there's some form of a flow field or flow direction surface that is generated. And then the features themselves are weighted as you move downstream. So we sought sort of alternatives and alternative ways of thinking. And for this, we started by thinking about the way that channel depressions were detected in the first place. So typically, tangential or planform curvature is used. It's probably the most common approach because it successfully identifies areas of convergent flow. These algorithms have known properties, and they're typically canned within GIS software. One of the things that has long been recognized is that these are local operations, taking advantage of only the 8 pixels surrounding any focal cell to understand whether a focal cell is in a depression or not. And so they're fixed to the scale of the DEM. As early as 2007, it was suggested that if you really wanted to adapt this type of curvature analysis to different types of terrain, you needed to first do an analysis about what the scale of the terrain features were likely to be, so you could resample your terrain and match that to the extent of the curvature analysis. So this technique really doesn't adapt well to all terrains, and it can suffer in human-dominated landscapes as well. A more recent technique was developed in 2003 in the computer vision literature that uses line of sight criteria. And I think one of the approaches that one of the outcomes of this analysis has been the kind of line of sight criteria you see used in modern video games. It's called topographic openness, and it measures the degree of enclosure or of particular features or prominence of those features in a terrain. The advantage of it is that it uses transects moving out in 8 directions from every focal cell to identify the feature at any particular distance that interrupts the line of sight. And because of that, it is not scale dependent, it's scale independent. It's sort of a self-adapting window that interprets the terrain surrounding the focal cell at every pixel. And while this is extremely powerful for visualizing topographic features, one of the things that we've found in working with it, and others have as well, is that the values are often produced by this, whether it's positive or negative openness, are often not very intuitive and difficult to interpret as a result. Whether one uses curvature or topographic openness, the whole point of doing this is to understand the values in any particular terrain relative to the whole distribution of values. In other words, to find extreme values of curvature or openness that might help indicate a process domain, a distinct process domain. In any landscape, most of the terrain is either hill slope or hillside or flat surfaces, and stream channels themselves represent a very small and relatively extreme topographic signature in the landscape. And so in practice, the idea is to use these surfaces, whether it's curvature or openness, to identify extremes that might be classified as channels. And one of the techniques that's been used is simple quantiles and sort of a QQ normal analysis. So this is an example of this. The black line here is a distribution of topographic values across a landscape. And the idea is to find outliers, some values that are very extreme that might indicate channels. The problem with that kind of thresholding analysis is that it needs to be developed for regional terrain, In other words, every different landscape probably has a different terrain threshold. And when humans modify the terrain, that threshold is about, not really appropriate. The threshold you get empirically is not really appropriate for finding streams. Instead, it tends to find the human-dominated landscape. In this case, there's an open pit mine in this image, and you can see when we use a threshold on openness or curvature, we end up seeing that extreme value is the human-dominated terrain rather than some other techniques that don't rely on a threshold. And that's where geomorphons come in. Geomorphons are a landform classification approach that was developed in 2013. It uses the same principles as topographic openness in the sense that it evaluates relative height of terrain or enclosure within 8 directions from any cell. And it tries to map the relative elevation that bounds line of sight in all 8 directions. And it's the pattern of that relative elevation rather than its degree that is used to classify every pixel into a landform type. So there's some examples here in the figures, and I wanted to go over them. So if you can imagine a terrain here, this is a figure from the manuscript. Many of you have probably seen this before. The focal cell is this pixel here in the middle, and you can see that we're sort of in a valley. And the idea is that the geomorphon for this pixel is the set of 8 neighboring features that are sort of bound that focal pixel in terms of line of sight. And those can be classified as either higher or lower or the same elevation as the focal pixel. And that leads to this 8 value code, which then is converted into binary and a distinct numeric code. And there's a lot of information embedded in that number. In practice, what you can see is that each pixel down a valley has a geomorphon associated with it that then gets classified and encoded. And there are many codes that are unique, but they can be compressed into 10 common landforms. And they're indicated in this figure here. And also in this list here, and they're really dependent upon whether the surrounding terrain is higher than or lower than the focal pixel. So if they're higher, it's red in the surrounding code. If it's equal, it's green. If it's lower, it's blue. And here you can see the number of lower pixels or bounds and the number of higher bounds. Today, we're really going to be focusing on the set of classes in the upper right corner here, valleys and pits. They're typically navy and royal blue in the geomorphon maps. And what I want to emphasize about geomorphons is that the parameters that produce them are adjustable, but they also generate a host of encoded information that we can take advantage of to map streams in a lot of different ways. And I'm only going to touch on a few today. So I want to give some examples. Here's some digital LiDAR terrain, and you can see that there's a broad floodplain in the upper left-hand corner, some tributary valleys encoded with the number 2, associated ridges and slopes, and some headwaters. And without doing much to the default parameters of the geomorphon code, we can produce a classified landscape map that looks like this. And you can see that the blue areas and navy areas are the fluvial features by and large, the headwaters, the channels, and some of the tributary channels. And those are the features that are of interest to us. But you can also see that it's detecting both broad features like valleys and also narrow features like channels. So it's possible to actually adapt the settings to focus on either one of those types or scale of a feature and better interpret the terrain. So I have another example here to show you. Here is a landscape that has been set to detect very broad scale features in the landscape. So here we're focusing on valleys, trying to understand the context where we might expect to find stream channels. When we scale out a little bit and look at broader landform features, we tend to see much more continuous features that look like stream networks. And this can be really helpful in narrowing the search for channel-like features in more detailed terrain. It's also useful if humans have really modified the landscape signals that we would typically use to find channels. And in this case, they have absolutely done so. There are actually only 3 streams in this map because this is a map of downtown Baltimore, Maryland. And what you're seeing is evidence in the terrain still remaining of buried streams, as well as the 3 major river channels that flow through the city. So it's possible to detect the signatures of water flow even without much detailed topographic information. One of the things that David and I set out to do at the beginning was to understand a bunch of different ways for detecting channel heads and how well we could map their features in the landscape. So this is a result of a study that we did where we mapped 5 physiographic regions: the Coastal Plain, the Piedmont, the Blue Ridge, Ridge and Valley, and Appalachian Plateau, and the Chesapeake Bay watershed. We also considered 3 land use contexts: forested, agricultural, and urban landscapes. And poor David, walked upstream in all of these watersheds and went to the headward extent of channels and then mapped them with a GPS. And then we mapped all of these landscapes using channel predictions that used curvature, negative and positive openness, their combination, and geomorphons. And we compared each of them with a number of different criteria, including distance to the channel head from the most upstream map feature. What we found was that most of these techniques produced reasonable results most of the time, but in general, some of them were much more sensitive to land use context and local physiography. So paying attention to those really mattered, specifically for things like curvature and openness. In addition, curvature and openness required relatively high labor-intensive filtering techniques in order to develop these maps. That involves regional thresholding, analysis of the size distributions of pixels that were identified as depressions, filtering them using a critical drainage area, and then linear networking. We produced geomorphons using those same approaches and got as good or better results. And we were also able to produce geomorphon stream maps using very simple automated techniques and just a single filter that produced channel networks as good or better than some of the other more intensive approaches. In addition to the benefits then of the ease of delineation, geomorphons also have attributes like dimensions and their shape, their land use context, and other diagnostic information that really help interpret the nature of that feature in the landscape. So here are some examples of the advantages of using geomorphons in direct detection. This is a landscape from Pennsylvania. It happens to be in a valley bottom that is dominated by agriculture, as I think you can tell. We have a stream threshold here with a 60-acre flow accumulation threshold, and it's now shown in pink if we follow that flow accumulation downstream. And you can see it captures the downstream channel, but also starts above where the channels start in the landscape. Whereas geomorphons detect where the channel is, including a ditch that is not captured effectively by the flow accumulation surface. Another advantage of geomorphons, as I mentioned, is that they have a dimension, and their dimensions are driven by the detail in the LiDAR. So they tend to map streams more precisely than coarser scale stream maps, as you might expect. And it is then possible to detect new streams that didn't exist, as well as map the existing streams with greater spatial detail. And once these features are mapped, it's possible to extract both the width and the depth of those features, as far as it exists in LiDAR, directly from the DEM. And we believe that this is better suited for a lot of precision applications that are driving the desire for high resolution hydrography. In terms of, so that's sort of like our take on feature detection and extraction. In terms of downstream tracing, Most folks accomplish this type of operation with a flow field, flow direction surface, typically as derived by most GIS packages. The problem with this is that it often requires a hydro-enforced DEM. That means that there needs to be some conditioning of the DEM ahead of time, whether it's filling sinks or breaching overpasses and bridges, or locating culverts, and that typically involves a lot of manual review and correction. The other problem that's less widely addressed is the idea that flow direction uses the steepest descent criterion. So it analyzes the surrounding 8 pixels from any focal cell and then directs flow that way. And while that's fine for many cases, there are some cases where it's limited in its information use. In other words, there's more information available that the algorithm doesn't have any capacity to take advantage of. So one of the problems for this is that the assumption is that flow is going to follow the terrain. And in some cases, that's not the way that the channel goes in real landscapes. So being able to take advantage of other pieces of information is really important, we felt, in our downstream tracing algorithm. Other people have noted this problem as well and suggested various alternative approaches, but most of them are developed on theoretical or sort of theoretical perceptions of natural landscapes and that have evolved under climatic change or continental uplift and erosion rather than human modifications of terrain. So they have limited use in practical application. What we've focused on instead is recognizing that any approach that maps depressions in the landscape is going to have discontinuities. So we expect them in the landscape. We expect there to be features that have discontinuities that are tracked, whether they're man-made features like the ditch in the upper right or the stream that's flowing from right to left. And then we have to find a way to connect those features in any resulting line work. But we can take advantage of both the upstream and the downstream location of channel features using our algorithm. So by knowing where the direction is that any flow direction algorithm is trying to get to ahead of time, we are able to cross any discontinuities in the channel feature map that you see here without hydro-enforcing the DEM ahead of time. So we can produce a stream map that is contiguous, that goes across bridges or through culverts, and creates a seamless linear network. So our simple methodology, which is modular and parallelized so we can run many watersheds at once, starts with basic LiDAR elevation, delineates valleys with a very broad geomorphon classification, then delineates a finer scale geomorphon classification to identify things that might be channels, selects the things that might be channels using the valley network that was identified in the broader geomorphon analysis, classifies them to understand which ones are most likely to be channels, and then connects them as a linear network. In doing this, we feel like we've sort of changed our focus. And so instead of thinking about what the optimal drainage area threshold is, we've really started to recognize that in the practical reality of this is there are a lot of features in most terrains that look like river channels that we may or may not want to include in any analysis of flow conveyance. And we may not want to map them in a blue line map. So rather than thinking about conditioning DEMs and routing flow and then predicting channel initiation and throwing away a lot of information, we feel like we can identify where channels are fairly robustly and connect them. But our focus now is distinguishing and identifying those channel features that belong in a stream map, the way that most of us are used to. Specifically a blue line map versus a map of all drainage features. So when this illustration here is just to show you that in an agricultural landscape, there may be things that we want to include in a blue line map, but there are other features that we're not so sure about. So if we look at the terrain, we can see channelized features and swales, and we may want to include some of those, maybe the green ones, in a blue line map, but it's unclear how much we need to include the red ones in a blue line map. And depending on the application, there might be a lot of interest in including those or not so much. So other features that we've noticed that are morphologically similar to stream channels and can disrupt any delineation technique would be rills and gullies, roadside ditches, some of which are really part of the stream network, others are not, agricultural ditches and swales with the same kind of criteria, detention features in ponds, floodplain depressions, so old relic channels, as well as oxbows, and then other features that are either anthropogenic in nature or in the bedrock, like crevices, slide scars for avalanches, or landslides and washes in desert terrain. So what we need, or we think we need, is an effective method for handling and classifying these different features for for production of different maps for different purposes, and then being able to adapt to different terrains as the landscape changes through time. How we're approaching this right now is we're sucking up a lot of information as we do our mapping, and we end up with features that are stream-like that have lots of information associated with them. And so using training data based on our own interpretation of what should go in a stream map, we've been able to develop a classification or a prediction that gives a probabilistic value to every feature about what it most likely is. And even if that probabilistic value is wrong, and it is from time to time, it is also useful to understand what it might be or what is confusing the algorithm, and then why. So what we use is a form of machine learning and artificial intelligence called random forest. We build a model that classifies channel-like features, and we can predict either whether it's a channel or not, and this is actually an empirical distribution from a part of Pennsylvania, or we can predict all of the different classes separately, and that's the output from the model here, focused on non-channel features. So we can then select, using those outputs, what we want to include in a blue line map. Here's a list of those non-stream classes. We think it's actually really important that we are mapping these at the same time and generating probability surfaces about what they are, so that we can use this information for other applications. Here's an example. It's not a perfect example, it's just an example of a number of geomorphon features that are identified through this process, and then typing. And you can disagree with the typing, but it is the model's prediction of those types, and then the resulting networking of a polyline as a result. This type of product is really useful also for understanding the types of features that are confusing automated algorithms, and it improves our automation through time. So once we have these features, it's possible to generate attributes, as I've mentioned. Each pixel has its own geomorphon attributes, and that's tremendously important for understanding the orientation and shape, and the extent of the topography that limits our understanding or limits the line of sight, and can be used to assess the consistency in a terrain signal among many pixels. We also have spatially explicit layers of channel width and bank height that are produced automatically through our process. And each feature or group of connected pixels can be analyzed independently based on its attributes. So like the depth and the bank height, how straight it is, whether it meanders, that kind of thing. And that information can be lost in reach scale summary. So in the visualization you see here, you see the bank height being used to identify a place where incision is occurring in the landscape. And that might be the beginning of a head cut, or might be where you want to stop mapping a stream versus a swale or some other type of ditch-like feature. I mentioned bank height. So what we're ending up doing is generating the height of the topographic enclosure for all stream pixels. So that tells us for every single pixel in a large feature like a stream channel, what that pixel's estimate of the bank is, which means we get hundreds, if not thousands of estimates for every reach of stream. And we think that distribution is really useful and can be analyzed for a host of geomorphic purposes, habitat purposes, and management purposes. So this illustration just shows a cross-section on terrain using a vertical profile tool to understand how it compares with the maps, the data that we're mapping. We're also generating continuous measures of channel width. So these are measures that vary with every, effectively a cross section as you go up and down the channel. So every cross section has its own independent measure of width. Another really useful channel dimension feature that we can document over very broad spatial extents. And this occurs automatically in our algorithm. We think this can be really useful for understanding how human-dominated landscapes are changing in response to the reshaping of the terrain outside of the stream channel. So in this case, you see a bunch of stream cross-sections indicating a particular tributary in this suburban stream is incised where its headwaters flow out of a suburban neighborhood. So these products, as I mentioned several times, are fully automated. They include the channel skeleton, the raster representation of the channel. This is a two-dimensional representation, but it includes discontinuities. They could be because of road crossings or karst terrain or other types of disruptions or even indistinct LiDAR returns. But it does mesh well with high-resolution land use cover data and imagery. And we have spatially explicit layers of channel width and bank height all along the network. We also produce a polyline stream network that's a 1D representation of the channels that connects the channel skeleton. It also can be segmented to identify portions of the line network that are in culverts, going over roads or under bridges, crossing open water, or just connecting in a place where the LiDAR doesn't detect a channel. In addition to that, there are a number of reach scale attributes, of course, that can be associated with it, and they're listed here. A lot of these attributes are really important for modeling purposes, and a lot of the reasons why researchers and academicians, in some case modelers, managers want high resolution data. One of the things that we think is really important about an automated algorithm is how it can release us from focusing on the act of producing a blue line network and really focuses on what we want to do with it and whether it needs to be edited in very obvious ways. So you don't have to be a very sophisticated technical person in order to see where there's a problem in the network. So these are some examples from Baltimore, where I live. In this landscape, you have a reservoir, you have a steep terrain going down to the reservoir. The upland is really dominated by suburban residential neighborhoods and some urban areas, strip malls. Consider the challenges of trying to map that in LiDAR terrain with man-made and natural features, road crossings. There is a dam in the upper right-hand corner of the image, and moving across open water. When we perform a technique, we generate a bank height map like this, and it provides sort of like the breadcrumbs that we want to use in downstream tracing. And you can see that there's variation in bank height across the landscape. The hotter colors are shallower and the cooler colors are deeper, as you might imagine. And what we're doing is connecting those with blue lines to get across the open water, to move across the roadways. And this is all done in an automated fashion in our approach. This is actually, in my experience, a relatively easy situation these days. A much more difficult situation is illustrated here. This is sort of like one of my worst nightmares. We're now in downtown Baltimore along the Patapsco River. Patapsco River was the center of industry during the Revolutionary War. It's a very human-dominated floodplain, in addition to the fact that it's surrounded by a city. So there's all kinds of ditches and swales and berms that have nothing to do with anything and are just there, and as well as all kinds of ruins, even in the floodplain, excavations from the floodplain that create signal. old railways, you name it, it's there. Oh, and the sewer line goes through this image as well. So consider those challenges in actually using terrain to make a blue line map. All of these things are going on. And so this is the skeleton we're working from. We're detecting all kinds of different types of features, and we have to make sense of this. And so right now our algorithm does, I would say, okay, could still get better, but it produces a blue line map that in some cases is actually detecting a buried stream up here. Here's a daylit portion of the stream, and then it actually does flow out and runs along this road right here. In other cases, I'm not sure whether that's actually a culvert there, but it does make that breach. And in some cases, it flows across the wetland in ways that I might not really like, but it does connect with this ditch between the highway, which is in fact what happens in the real world. So we're getting a lot of different lines that we can try to make sense of and understand the nature of delineation in very difficult terrain. So I think this is really interesting and an avenue of future work. So right now what we do is we parallelize this and we run it on a Huck 8. Here are the Huck 8s in the Chesapeake Bay watershed. And we run this in parallel so that all the Huck 10s or 12s are processed in parallel when we run each individual Huck 8. Usually denoising takes between an hour and 8 hours and only needs to be done once for any terrain. And then we can typically produce channel extraction for a Huck in somewhere between 2 to 6 hours. This is easily repeated, and we can update it for various reasons. And this is important for different terrains because as we've moved out from the Chesapeake Bay watershed, we've been encountering new features that we didn't see in the East Coast. Shock, I know. And that requires us to think through some of the assumptions that are embedded in the algorithm, which, because it's so rapid, are relatively easy to correct. So the inputs that we use are the LiDAR terrain, but we've also found that high resolution land cover is essential for making automated informed decisions. So when we look at terrain, a lot of times we are in fact, and interpret it, a lot of times we are in fact making sense of the landscape around the stream channel, and the computer doesn't have that information. So we found that providing that information to a computer actually improves the delineation process quite a bit. I'm not sure to what degree that's on people's radar right now, but we found it very useful. So this is just an example of some stream maps we've been generating in different kinds of terrain. We don't typically find mountains like this in the Chesapeake Bay watershed. This is on the Stillaguamish River in Western Washington. Thanks, Josh. Still working on that. And this exercise has been where we're working with the Washington Department of Ecology has been really important for helping us understand different types of features that can be produced in different terrains and how our algorithm can be generalized to these features, whether it's very steep snow-fed systems or very broad floodplains with lots of relic channels and terrace features. That's been a really interesting exercise thus far. We've also done work, as I mentioned before, in Arizona, and in Pima County here, we have a lot of washes to deal with, but we found that even though we might not pay attention to washes like this in thinking that it's tributary to a stream, Pima County managers are really interested in this type of feature because it is where the water flows and it also has huge implications for infrastructure. So some examples of this are where washes cross low-lying roads and make drivers vulnerable to being hit by flash floods, and also identifying places where infrastructure itself is rerouting water in the landscape and may change the way that water gets from place to place to place. Probably one of the most interesting discoveries in working with some folks at the NRCS is that there are a lot of water control structures that are remnant and in the desert landscape. And by virtue of mapping streams in this landscape, we're also able to map those water control structures with a high degree of accuracy. So here's some examples of relic berms and dams and grazing ponds highlighted in pink in LiDAR terrain. So I'm wrapping up here. To summarize, we we feel like the new elevation data sources that are out there provide us an opportunity to rethink how we approach stream delineation, what features we map, and which attributes are important to retain as we do so. We think that the geomorphons provide a rich data source for mapping, and that the new applications we're able to generate with them are enriching our hydrographic data models. And those enrichments are leading us to new applications and new synergies, connections between hydrographic mapping and other forms of terrain analysis. So we're really excited about it, and we hope you are too. Thanks very much for your attention.
Thank you, Matt, so much. I am not a hydrographer, I'm a landscape ecologist, and this just made so much more sense to me than other bits of hydrography. We're going to go ahead, if you're okay, and open it up to questions from the participant. And I think Phil, can you go ahead and feed Matt any questions that we have?
Yep.
Oh, should I keep sharing so that I can highlight particular slides if people want to see them?
I think that's a great idea. Thank you.
Sure.
Okay, Matt, first question is for me. Have you been able to automatically detect karst areas using your process?
Well, we haven't run our algorithm with the intention of identifying karst areas, if that's what you're asking. So, but one of the things that we've noticed is that when we are operating in karst terrain, there are the extent of blue lines that are actually associated with a channel feature changes fairly dramatically. In other words, the algorithm that we run doesn't know not to connect them across really large flat features. And so it does produce connectors that have no channel associated with them for long extents. And so essentially there is a signal in the output of our data that we can use to detect karst, but we haven't actually done it with that purpose in mind. Does that help?
Yes, I assume you're implying that it could be refined to attempt to do that.
I think so. I haven't tried it yet and I haven't explored it, but I think we have sufficient signal and it's distinct enough from other terrains that you could use it to flag those landscapes. We've been really focused on what to do about those connectors in terms of whether we want to keep them in a blue line map, because we know that people are going to say there's no stream there, and they're right, there is no stream there. So we have to think about how we want to handle those types of terrains and if there's any refinement we want to employ. But I think that the signal is there in the output.
Well, if you ever want to try it on some land, I got some property in Indiana that you can look at.
Okay, I thought you were going to say a bridge in Arizona. So, okay, good.
Next question from how important is temporal resolution to the model? Can you run it with just one set of flight data?
Oh, that's a great question. So I may have misspoke in talking about temporal data sets, in that I think temporal data sets are really interesting. And I think having kind of an automated or objective approach that you can apply is a really useful thing in order to assess landscape change with temporal data sets. But temporal data sets are not required for the delineation method that I described today. So you can do it for one LiDAR flight, if that makes sense. One point in time.
And I would invite anyone who, if folks have asked these questions, if you want to come off mute and expand on them, please feel free to follow up after I go through and list them in chat. So please feel free to come off mute.
And hi, this is Becky Anderson. I just wanted to give a little bit of context to so from USGS. Matt, thank you so much for the amazing presentation. I also, like Linda, I'm trained in landscape ecology, and all the things you say make so much sense to me. And it is exciting because we do have features in the NHD now, even like area of complex channel, that are really a lot more geomorphic than anything else in what they kind of attempt to map. For everybody else on the call, I just wanted to give some context with 3D hydrography program and this work. So we asked Matt here to talk particularly because a lot of these geomorphon methodology basically came up a few presentations back with Josh in Washington, I think. And we thought it would be really great to give everybody a better technical background or a kind of an understanding of exactly what we were talking about with geomorphons. So we definitely don't expect you guys, everybody to run out and start cranking through this stuff yourselves, but you may be working with contractors, you might be working with other technical people, and we wanted to make sure that we're all speaking the same language here. So just wanted to kind of give some context. Again, thanks so much, Matt. That was fantastic.
I'm glad that you enjoyed it. And I have to say that I probably am speaking to the landscape ecologists in the room because I'm also a landscape ecologist, although I was trained in aquatic landscape ecology.
What do you consider as high resolution land cover?
That's a good question. I would say that what we found really useful in our delineation technique is being able to see open bodies of water, and that includes large rivers like the Susquehanna, but also things that are smaller than that. When we started developing this algorithm, we really were focused on finding headwater channels, thinking that that was where the need was greatest. But this is when we first developed the method, I would say. But then as we started looking at applications like mapping streams across the entire Chesapeake Bay watershed, it was really important that we were able to capture larger streams as well. And for that, using mapped water bodies and open water was really important because a lot of LiDAR is hydro-flattened, and that can confuse any terrain interpretation of where water flows. And so as an ancillary source of information, the open water is useful. The other thing that we find really useful, it's not, I wouldn't say it's critical, but I think it's useful, is if there is that high resolution land cover involves a road map. In other words, there are roads that are visible in the land cover map. What we typically do in order to identify culverts is we can track whether the blue line mapping that we're doing, that connection is going over a ridge or over a road. And that is a useful piece of information for detecting culverts and making connections. So that other piece of information where impervious cover is particularly roads, is quite useful.
Great. Oh,
So to answer your question, if you can detect those features in the land cover, I think that's what's most useful to us. Sorry, we've been working with a 1 meter data set in the Chesapeake Bay watershed.
So it's a custom developed land cover.
It was done by the Chesapeake Conservancy in consultation with some folks at the University of Vermont. I think we could probably get by with a slightly coarser data set, like 5 meters. I don't know what would happen with 10-meter data set, but we could try it. I think it would be possible, but maybe not quite as accurate.
Will you be sharing your slides with the group?
Sure.
Okay, great. And we obviously will also have the recording on my NSGIC. Can you go back to the last summary slide again? I think someone wants to ask a question about it. Okay. While people are digesting that, let me ask this next question. Is this packaged in a tool, or is the method or code available to the audience?
Not yet. We are still developing it and making sure that it's generalizable across different terrains. So for example, I wouldn't want to give you the package that we have for the Chesapeake Bay watershed if you live in Wyoming, just because I think the features would be different. But our intention is eventually to make this publicly available so that people can map streams across the country using this approach. And I think if we wanted to release it publicly, we'd want to make it user-friendly, which I don't think it is quite yet. And then also have particular parameter sets that could be adjustable and customizable for different uses. And exactly what those are, I don't know, because some of that will depend on how the algorithms perform in different landscapes. Does that make sense?
Yes. Kind of a follow-up to that, what hardware, what computing resources are you running this in? What kind of an environment?
Well, our intention in mapping was to make this as open source as possible, so that it would be, people could use it without buying an expensive software license. So it's possible, we've been using the functionality that is embedded in GrassGIS quite a bit, or QGIS, I guess. But the actual software itself is encoded in Python, and then so an environment that it runs Python and then can operate GrassGIS would be necessary. We have run it on our sort of desktop PCs, but for large landscapes, it's a lot faster to run HUCs in parallel. So the times that I was giving you are a result of running this algorithm on a UMBC's supercomputing system. So we typically take advantage of something like, oh golly, we have up to 60 or 70 nodes at our disposal, and each one of them can, or cores, I'm sorry, and each one of them can, sorry, nodes, and then each one of them probably has about 15 or 20 cores. So we can run a lot of HUCs at the same time, if that makes sense.
Yep.
I don't think that's necessary, but it's certainly makes things go faster.
And have you experimented with different LiDAR point densities?
No, so far, that's an interesting question. And then about like the quality of the LiDAR. So far, we tried to use QL2 LiDAR, and we've kind of stuck to even resampling it so that it's all at the same point spacing, so that we can sort of, at least in the Chesapeake Bay Basin, use the same kind of scale parameterization everywhere we go. But I think it would be an interesting question to see how modifying the LiDAR quality or the point density influences the output.
So I'm going to invite Sean Vaughn from Minnesota to ask his question, because I'm not sure it's a question.
Yeah, thanks, Bill. Yeah, it's just more of a comment. And Matthew, thank you. Appreciate the presentation, like so many here today. My statement there is really about the need or the awareness to have a community of practice around what you're describing today. There, many of us in this attendance list have come together over the years, and we've seen different presentations like this. I personally think yours is one of the most innovative and something we can really start to implement. But all of us, so many of us, have to sell, we have to market, we have to get approval to implement anything. And so I've been involved in this type of work almost as long as you, Matthew, and I've practically built a career around trying to figure out ways to get high-level decision makers to support work like this. So many people in the last 25 years that I've been involved with, they see everything as a map. And thankfully that the LiDAR technicians and the GIS hydrologists like myself are starting to rise to the top. And where I'm going with this to say that a presentation like this that uses the language of channels a lot, takes a lot of those decision makers' minds and locks it into a map and classification about ephemeral and perennial and intermittent. And really, I think what you're getting at and what we're trying to strive for in the state of Minnesota is recognizing that LiDAR captures water conveyance landforms on our surface, which convey water, which convey the chemicals, the contaminants we're trying to mitigate. And so my question this is not a question, is what I'm trying to say. This is a statement of support for work like yours, Matthew, and possibly others. But more importantly, that we use this venue to get going really quickly, to start to build a community of practice of language about how we communicate about this stuff, and really step away from our past and our history that's locked into those older classifications, so that we can start to implement and be innovative on what we're going to do for mapping next generation hydrography. And I guess that's what I wanted to say in just relation to the word channels. I just happened to select that as an opportunity of words to focus on.
Well, thanks, John. That was wonderful, and I really agree with where you're coming from. One of the things that drove my interest in this particular mapping problem, which is about making a map, is that the power the maps have. So a couple examples. One, the Chesapeake Bay Basin does a lot of work on riparian buffers and forested riparian buffers, as I'm sure most states do. But one of the things that doesn't resonate with a lot of folks is that the original studies that demonstrated their impact, riparian buffers impacts, were done, some of them were done in Maryland, and the streams on which they were performed, those experiments, don't show up on any stream map. And again and again and again in suburban development around Maryland, I see places where development is going in and burying a headwater stream, and they are able to do this because nobody maps the headwaters, because they don't show up on stream maps. And those things are the water conducting surfaces and systems that can then get rerouted into storm sewers and then shunted into gullies and cause erosion and conduct pollutants all throughout the landscape. And so my hope is in participating in this group that I can accelerate the process by which we generate maps and information about the terrain to help us understand what it is that we're doing when we convert the terrain hydrologically, chemically, and geomorphically. So thank you.
Matt, I think we need to put you guys in a room together at the next NSGIC conference. It would be a great conversation. Question, are you incorporating any of this work into the USGS NHD?
Well, we hope to. I mean, we certainly want to see the next generation NHG make use of LiDAR, as I'm sure all of you do. We'd like our line work to play a role in that. We're looking at ways to do that. There's the idea of conflation and sort of linking the attributes of the existing NHD to any new map that you make. And we don't have that automated yet because I'm not sure that we all know exactly what attributes need to be in the next generation NHD. I know there's some guidance out there, but it just seems like that's an area of growth and a fruitful area for discussion. So I'm looking at ways to do that. I think one of the things that's nice about the data product that we are producing is that it does have a lot of information in it that can be used to inform the conflation exercise, but not everything. And so I know there are other folks that are really interested in working on that problem too, and I hope to work with them.
Great. Next question. How did your geomorphon process perform in areas of no LiDAR returns? I guess where DEM interpolation estimates and no actual returns dominate the elevation surface.
Ooh, that's a good question. Well, so the way I've sort of described this all along is that I don't expect any method that we use to perform all that well if we don't have any information in the LiDAR. So that means if there's something disrupting the surface, I guess I don't, or there's been hydro flattening or something like that, I guess I don't expect the technique to work well, and we need to develop a way of handling that. We've been focusing on open water because that's one of the common places where there are problems. Trying to think if I've seen places where there is interpretation or interpolation. I know I have, and just what happens there. So often what happens, I think, is that we lose the channel signal. In other words, we don't see a channel feature being mapped. And because our algorithm is taking advantage of knowing where upstream and downstream is, we can sometimes traverse that area of interpolation. We get across it. Whether we get across it exactly the way that I would want it to be if I was looking at an aerial photo, honestly, it's not always that way. So, but that's for me an opportunity to learn about what it is that what signal is being fed to the algorithm and how it's responding. But I don't know that it's always going to be successful in that terrain.
Yeah, Matthew, I was thinking of primarily areas where we have high vegetation coverage and you don't always get a good penetration to the ground surface. So
that's absolutely true, especially in coniferous vegetation or very dense vegetation underneath the canopy. So I think one of the things that, well, it sort of depends where that happens. But there are sort of broader signals in the terrain that the algorithm would probably make use of. We constrain our channel networks to be within the valley. So if there is a valley, a broader valley, then that would be used to constrain where the water flows, if you will. But the other thing that we're using is sort of a least cost path approach to think about trying to get to the next downstream feature. So in some cases, it may be a straight line connection. And I guess what I would imagine doing is extracting over that line where we don't have a feature, some information about what the quality of the LiDAR is underneath that line to help identify those locations.
Also, how do you determine how far to connect those upstream and downstream segments?
Well, we don't have a limit on that yet. We try to constrain it with topographic information, so it's not just distance, it's also distance and topography, because otherwise we'd have connections over topographic divides. We try to avoid that in stream maps. We like the water to flow downhill most of the time, but we do find it's useful for short distances. So often what we do is we compare the discrepancy, if you will, between the terrain-based line or connection and then a least cost path line, and try to understand the information embedded in those differences.
And I think you just answered this one. What method do you use to connect the channel regions?
I think I did.
Yeah, okay. Have you ever tried this algorithm with photogrammetrically derived mass points and break lines? So basically a different input than the DEM.
No. I mean, I don't know what that would do. I'd be curious. If you have a data set you'd like to test, just let me know. We've got a lot of these kind of explorations going on, and I can only handle so many at a time, but it is a question. If there's a real need for it, then we'd be willing to give it a shot.
How are you evaluating the reliability or accuracy of the mapping algorithms? That's
a great question. So I think one of the questions I'm supposed to answer later is like, what would I do differently? That question is challenging for me, or was challenging for me at the outset, because I didn't know what we were going to produce, like what the different ways we could compare, right? I knew conventional methods of assessing validity of a stream map. So one of the ways we could assess it is by how many reaches are correct, right? But since most of them are pretty easy to identify, then that sort of biases our output. And we could focus on like how many headwater streams we hit, or how many really difficult reaches we get correct. And that would kind of bias it in a different direction. So I don't think there's one way that we are interested in assessing the validity. A lot of what we've done so far is image-based. Does it pass the LAF test? And then looking at other sources of information, including existing line work and alternative line work. And what we plan to do for the Chesapeake Bay watershed is let local people with local knowledge tell us what's wrong with our maps, which is always a fun exercise. But I think it's in many cases, when you're doing this kind of delineation, you've got so much invested in any particular delineation, that's a really hard thing to hear. But because in our case, we can actually retool large areas of the landscape and redo them, overnight. If we learn that there's a process or systematic problem in our map, it's a little less of a concern for us. And we're actually quite interested to hear about, okay, we think this is pretty good. What is it that we're missing? That kind of thing.
Great. Have you tried integrating urban storm sewer networks into your processing?
I think we would like to, but so far we've been tasked with covering such large areas that we haven't tried yet. We're just trying to get the line work out. But in order to make the product useful, I think bringing in any information or sort of developing ways of bringing in that kind of extra information is really important. Right now, we don't have perfect information about storm sewer networks. As I think I showed you that map of Baltimore. Well, most of the sewers in Baltimore actually follow the terrain by and large, so they don't really switch over very much between basins, but they do in certain places. And when they do, we totally don't see that. So we would need that data to correct the line work that we produce. So no, we haven't done it yet. That is something we can do in the future, I think.
And finally, before we go to the summary, when you mentioned the attributes of width and depth, is that of the water feature, or would that be from the top of the bank?
So we're measuring the width from bank to bank. So that's the feature itself, but the feature itself is delineated by pretty close to bank most places. I guess it sort of depends on the bank angle a little bit, but usually what we see is that the top of bank is where the edge of the feature is. So if you have sort of like a pyramidal channel or trapezoid shaped channel, we wouldn't see the channel bottom so well as much as the top of bank, if that makes sense. We're probably delineating the top of bank width, and then we are when we're doing bank height, we're getting estimates from every individual pixel. So we see both the bottom of the channel to the top of the bank, to the extent that there is a bottom of the channel in the LiDAR, as well as sort of the sidewall heights. And all of those are integrated into our averages. Yes, with green LiDAR, you would certainly be able to see into the channel, but we don't have that everywhere.
Great. Okay, Linda, back to you.
Thank you so much. And again, thank you, Matt. We don't have a lot of time, but I thought we'd just hit these quickly. I do have a closing slide. I want to update people on our schedule. So you want to touch on these? What would you do differently this time around?
Let's see. Well, one of the things that I did when I developed the budget for this project in the Chesapeake Bay watershed was I thought that we were going to be making maps sooner, and it wasn't clear to me how easy it was going to be to automate it. And I think one of the things that we've done throughout the project is we've sort of adjusted our timeline to kind of develop an automated approach, because we think that in the end, we're going to be able to get better, faster with an automated approach. So I would have gone for that sooner than I did in this project. The other thing is that I budgeted a lot of time for kind of validation of the line work at the end of the project. And actually, I think I needed to do that early on with sort of in limited samples of the areas we were working on. And I ended up doing that. So I did do something differently than I planned, if that makes sense.
That's fine.
Yeah.
What surprised you during this process? What was the unexpected lessons here?
I think I touched on this already. I thought about this, and I really feel like it surprised me how many features in human dominated landscapes can look like channels. I mean, and how many there are, and even things that aren't intentionally created to route water could still look like channels. They just repeat so many times in the landscape. I think I'd noticed that in some kind of subliminal way in the past, but when you actually quantify them, there's a lot more than you think.
Very good. What resources other than data, whether it's documentation, some online resources, tools, what did you find really valuable or useful in taking on this project? Could be partnerships.
Certainly my partnership with the Chesapeake Conservancy and their efforts at high resolution land cover mapping has been useful. I think that there is there are a lot of people interested in streams and valleys and mapping for a host of different purposes in the Chesapeake Bay region. And so that network has been really useful for finding like-minded folks. I think some of them are on this call today. And I think that that's been really helpful for discussing the challenges they're finding or running into, but also in kind of developing a network, like I think Sean was mentioning earlier. And it's been really very interesting to hear from folks like this group that have much more of a national or continental perspective. And I think that it's really helpful. I mean, I've lived in the West and I've lived in the northern part of the United States and the Midwest and New England, and now the East Coast and the South. So I've been geographically mobile, but it's still really very helpful to hear people's perspectives from different parts of the continent.
Very good. I'm not sure this is relevant, but what resources would you recommend for others? You've mentioned the use of the QGIS and the GRASS and in Python. I know that's specific to the work that you're doing, but are there generally resources out there that people would benefit from knowing more about?
Well, I think we've really tried hard to keep our methods and even our validation so far to be connected to things that almost anyone is going to have access to. And we've done that purposefully. In some cases, other folks may have data sets or access to software or something that we don't have, and that's been and that they might benefit from. I think that I did not realize how helpful it was going to be to have Google Earth imagery, especially the temporal image feature for validating hard to detect features and understanding what they might be. When I had undergraduate students looking at our initial maps, that tool proved really useful for communicating and learning about what the algorithm was doing and also what people do when they look at imagery. Yeah, even if they're trained.
Well, thank you so much. Really appreciate it. As most of you are aware, we will follow up. We're going to create a Q&A document based on this discussion because so much of the information comes from your questions. We will follow up with Matt to get that edited and published here in the next month or so, if he's available, because he's kind of busy running the university right now. So.
Not well.
Just an update for folks, as most of you know, the 3DHP forum is the third Wednesday of the month from 3 to 4:30. We mentioned that's a new time for us. Next forum would normally be in February, but because in the NSGIC mid-year meeting and innovation summit is that same week, we're going to encourage folks to attend the meeting. That's virtual and in person if you're in and around Milwaukee. And then as a reminder, in March, then we'll be doing our interest group meeting. So we won't have another active forum until April. And as I mentioned earlier, if you have ideas or projects that you would like to present, please do so. Matt, I'm going to encourage you to look at the chat because there's just so much positive response, really fascinating stuff. And I think a lot of us are envious of the really innovative work that you're doing. So with that, I will thank you all for your time today. And we'll see you next month at the conference, hopefully.
Always looking for partners.
Thanks, Matt.